Hi. Good evening, Trisha. Trisha, so how has your couple of weeks been? I am very sorry. I have been very busy with work in the last week, and I have not had time. And the week before that was illness. I'm very sorry. I know that you wanted to complete the syllabus as early as possible, but things have been a little bit chaotic and a little bit tough the last tight, so to say, not tough, tight in the last couple of weeks. So now the good news is this: I do have the next 2-3 days quite widely open. The question here, which I have regarding your timings, is this: what are your general timings with respect to sleeping, waking, that type of thing, basically?
Tomorrow.
Because I will be busy fully from 10 to, let's not call it 10, let's call it 9 o'clock in the morning till say evening 6:37. I will be tight. That is, other than that, I'm free. So, what timings can work?
After 6:30 is fine. Tomorrow.
Tomorrow after 6:30 will work for you, sure?
Yes.
Okay. And all right. Till what time will be feasible tomorrow? 6:30 se leke?
8:30.
8:30. All right. Let's try.
Until 9 also. If I don't have physics class tomorrow, then we can extend it.
Okay. All right. So before we start off, I want to have a quick list of the topics which are left over for discussion overall, so that I have an overall list to basically start ticking through. So can you give me what topics are left over from a discussion point of view, list type of thing?
Like in this chapter, you are asking.
Give me total itself. Let's aim for total itself.
इलेक्ट्रोकेमिस्ट्री के बाद वो डीएफ ब्लॉक का हाफ पार्ट इज रिमेनिंग.
Then chemistry and then D&F block NCRT ka part over there regarding the oxo ions.
Then we can brush through physical chemistry.
Which parts of physical chemistry? Because you have to be more specific than that. Physical chemistry pura
SCP, solutions and colligative properties.
Solutions and
colligative properties.
Okay, all right. Okay, so solutions, we'll have a quick brush up on that. All right. And any other topic?
No, itna hi hai abhi to.
I think organic maybe thoda baki tha, which was acids and bases.
That order of
carbocations, etc. GOC basically. Okay, all right. और क्या बाकी था बेटा?
अभी तो इतना ही है.
अभी तो इतना ही है. All right, so all right. Let's continue here. So इसमें we have discussed ionic to an extent, correct? Ionic एक जगह तक हो गया है, and electrochemistry में then you should be having a lot more clarity by now, right? You have tried out. Let's see. So what do you want to discuss today, beta? So we have electrochemistry का जो भी है, D&F block, CRT, solutions, and organic. These are the main things. Okay, all right. So let's continue on with electrochemistry, or which topic do you want to discuss today?
The cells we can do, or dry cell wala part.
Okay, so you want to continue with electrochemistry and usme discussion on cells. Okay, all right. So you want to continue with electrochemistry, correct? Okay. Now then let's. Okay, all right. So we will start with electrochemistry. Fine. So electrochemistry, ma'am. Can you now go into? You mentioned something about cells. What other topics do you want to discuss? in this
We
chapter?
have dry cell, lead accumulator, and fuel cell, and we have molar conductivity और कोल रोशेस लॉ भी है तो इतना ही बचा अभी तो
ओके, सो बाकी जो भी है तुम्हें आता है ऑलरेडी, इज इट करेक्ट इस चैप्टर में?
yes, you taught actually last lecture.
ओके, एंड मुझे याद नहीं है एग्जैक्टली कि क्या क्या टॉपिक्स खत्म हुआ था बेटा, सो दैट्स व्हाई oh, I'm not sharing screen yet. Okay, that was stupid of me. Let me start sharing the screen. Yeah, sorry, I was writing it down. I was assuming I was sharing screen. Uh, yeah, Dikram?
हाँ
हाँ, so electrochemistry, उसमें cells, dry cell, fuel cell, molar conductance. What else is what are the other topics which you have in the chapter which are pending?
कोल रोशेस लॉ
Cole-Roche's law, okay. And yeah, anything else?
conductance in solutions
Basically conductance में एक discussion.
हाँ
हाँ, ठीक है. And up to what depth, that is why I want to know what exactly do you need there. Conductance में एक discussion, what all are there, small subtopics क्या क्या तुम्हें है syllabus में, वो मुझे बोलो, because मैं conductance में घुसूंगा तो घुसूंगा अंदर. So if you give me the
like
subtopics which are there, there will be like guidelines along which I should go.
con except we have like that formula वो जो फॉर्मूला है उसके ऊपर ही क्वेश्चन आते हैं जस्ट लाइक डायरेक्ट फॉर्मूला
हाँ, tell me which terms.
why strong electrolyte, weak electrolytes, and
इक्विलिब्रियम कांस्टेंट कैलकुलेशन कुछ आता है कि नहीं?
नहीं मैंने आपको PYQ भेजा था तो
ठीक है, मैं देखता हूँ. कैन यू हाईलाइट द मैसेजेस एंड सेंड अगेन? Anyway, in the meantime, just tell anyway. What exactly are the other subtopics you have?
in what?
Other subtopics you have in this topic, in this chapter here.
That's all. Oh, yeah. इतना ही है.
इतना ही है, ठीक है. Galvanic cell. So let me just directly go to WhatsApp and have a look here. That will be easier. So maybe here. Okay, so electrochemical cells may you guys have. These are the toughest questions you guys face?
These are actually PYQs.
These are the toughest questions you guys face normally?
I find it tough, but I don't know about others.
I'm asking honestly. Just give me a realistic estimate so that I'll know where basically.
I haven't actually solved all of them.
You've solved all of them, is it? These
No,
are like
I
roughly, what to say, like 70% then.
No, I haven't solved any.
Oh, you haven't solved all of them yet. Okay, all right. Okay, all right. I see where roughly the level is at. Okay. Hmm. Okay, so where did we discuss till last time? I remember we had discussed about potential last time. So did we talk about what is meant by reduction potential, what is meant by oxidation potential, what is meant by potential in general? We talked about it.
Yes.
Okay, and did we discuss delta G and potential, or where did we go?
Yes.
We,
We did.
we discussed delta G and potential, correct?
Hmm.
Okay, so I discussed the relationship between delta G potential and Nernst equation. Somewhere till there, is it?
Yes.
And the RT by NF, that derivation was,
Hmm.
I suppose, yes.
Yes.
Okay, and okay. Okay, so we are at like 1/3 of the story right now. Okay. तुम्हें कंडक्टेंस भी है बाकी. Okay. ठीक है. I think I have a reasonable idea as to where things are. Questions के हिसाब से it is not that complicated of a thing for you guys, honestly. But if you want to understand, it will be a good fun thing. But I think we will limit our conversation with respect to this set of PYQ here. So the PYQ is like at least this is a proper full complete PYQ. Yeah, is it going to be like incomplete?
No, full.
All questions are there.
Probably. रहेगा most of the questions.
All possible questions in the exams which you write are here, correct? Okay, ठीक है, चल दो. चलो, we will continue on with the discussion here then. So cells, dry cells and fuel cell में तेरा issue है थोड़ा बहुत, and यहाँ पे भी है. And okay, all right. So let's start off today's discussion now, beta. So let's continue the electrochem. So electrochem is what you want to continue on, correct?
Yes.
ठीक है, okay. All right. Let me first. Do you remember when we had the last session, Gana? Last week, na?
Or last Sunday.
Last Sunday, that was on electrochemistry?
हाँ.
Okay, so that should have been 8th, I suppose, correct?
Yeah,
Time was your class, morning or afternoon?
Yeah,
Afternoon,
that only 2:15.
अरे let me quickly see क्या क्या हुआ. That will give me a better understanding as well. Okay, so we had discussed what is the reference there, how do we calculate. Okay, potential क्या है पूरा discuss किया है. Okay, we talked about electrolytic and electrochemical as well. Okay, all right. We had discussed the delta G link over there properly. Okay, all right. Then we had discussed this also. Okay, we had discussed the potential aspect. What is the Nernst equation? Actually, I'll continue the discussion here itself on electrochem. This will be easier. Okay, so net useful work done. ये भी हो गया काम. And ये भी हो गया. Okay. Okay, so now according to what I saw next, we'll have to talk about what is going to be a cell, which is basically what you mentioned exactly. So let's continue there. So when we are talking about an electrochemical cell, so if I'm talking about an electrochemical cell, An electrochemical cell is going to be something which is going to be one which produces electricity. So when we talk about a Daniell cell, this is going to be a typical electrochemical cell. So Daniell cell is going to be an example of a typical electrochemical cell. All right. So when we talk about an electrochemical cell, in the previous session there, over here, as you can see in this part here, we had talked about how an electrochemical cell is generating electricity, which basically means delta G is negative for it. And of course, the E naught of the reaction is going to be positive for it. So when you're going to be having an electrochemical cell, it is going to be something where the delta G for the cell reaction has to be negative, which will automatically lead to the electrode potential, not necessarily at naught condition, sorry, the electrode potential of the reaction, cell reaction, being something which will be positive here. So far, is this clear, Kana?
Yes.
Okay. So we are going to be having delta G of the reaction being negative and the E of the reaction, the electrode potential of the reaction being positive. How are they linked up? They are linked up by this equation. Delta G is minus NF into E of the reaction. So in this case, delta G of the reaction, or we can think of it as delta G of the cell. Now, when we say cell, what is the idea of calling it a cell? The idea of calling it a cell is basically, it is the easiest way to measure. Say, how did all of this start? All of this actually started not because scientists were looking to exploit electricity. See, when we started doing all of this, we didn't know how electricity was going to be useful for us. We were scientists at that time. They were just experimenting because this was being useful in some other ways. For instance, in this particular case here, this delta G of a reaction, these things over here are actually, the electrode potential actually started off as a way for scientists to study chemical reactions. That is, advances in electricity started happening from chemistry actually. So when you look at physics over there, physics may a full branch, multiple branches have opened up in physics through chemistry basically. So what happens over here is, this is going to be the starting of how electricity was discovered, or rather how electricity was used in the beginning, because electricity was like the niche experimental thing which people do not normally have time. So that was used only by scientists at that time. They were studying chemical reactions using electricity. So what this E of reaction was doing was, it was quantizing the tendency of a reaction to happen. So E of a reaction basically is going to be nothing but it quantizes the tendency of the reaction to happen. When I say reaction over here, I am only talking about the forward direction of whatever reaction we are trying to consider here. So when I say this particular tendency of the reaction to happen is being quantized, that basically means we are quantizing the tendency, yes, of the forward direction point of view of the reaction to happen. So far is this part clear, Kana? Or do you have a question over here? Any doubts over here so far?
No.
Show me your face, because ultimately I can't decide based on just your voice. So what questions do you have over here? Do you have proper understanding as to what we have discussed so far?
Yes.
You understood what I mean by quantizes over here, correct?
Yes.
Okay. All right. Now, all right, let's come back to the next part over here. So this is going to be what we are trying to do over here. So the delta G of the reaction here is something which they could measure in this case here using. So what they were trying to do was, this particular E of the reaction is actually a way to measure this particular thing. A chemical reaction was being studied where they tried to study these chemical reactions based on the tendency of the reaction to happen. So when scientists started studying how a chemical reaction happens. Or other chemical reaction, why does it happen? So when you start studying why something happens there, you have to start studying effectively what there. You have to start studying tendency for a change to happen. Correct? You have to start studying tendency for a change to happen. For instance, let me explain this a little bit more clearly here. If I'm considering, say, a chemical reaction. Okay. Now, imagine you're a scientist. You're studying a chemical reaction right now. So when you're studying a chemical reaction, you want to know why this particular reaction is happening at some point of time. You'll study, say, multiple things about it. You'll want to know why it happens. But when you want to know why it happens here, this is going to be having a unique reason for why it happens, correct? Each individual reaction which happens has a unique reason why it happens. Correct or not? Think. If I'm going to be looking at a combustion reaction, the combustion reaction has a different reason of why it happens compared to, say, a melting of ice. So every chemical or physical reaction, if I'm going to be trying to consider why that particular change is happening, chemical reaction is actually something which initially they started considering for physical and chemical. But if I'm studying a chemical reaction and I want to understand specifically why it is happening there, I need to start having some kind, if I want to start that study even, I need to have some kind of a metric. That is basically what your electrode potential series basically starts off from. I think we had talked about this in the previous session also partially. So I'm assuming this part here, we are going to be clear on. Yes?
Yes.
Okay. Now, the next thing here is going to be, when you're going to be looking at producing electricity here, you're going to be having only certain types of cells being meaningful. For instance, this Daniell cell which we had over there was something which was capable of producing electricity. That was the first one which was basically used. So can you tell me a little bit more about the Daniell cell? Do you have Daniell cell in your syllabus?
Yes.
What do you know about the Daniell cell, beta? Can you tell me what is the anode there? What is the cathode there? And let's proceed. What is anode in the Daniell cell?
Zinc
Zinc.
and cathode is copper.
Now, when you're mentioning things, you have to mention with their physical states. So zinc what?
Zinc rod, solid.
And cathode is?
Copper. Copper solution.
Cathode is copper solution or copper rod?
Sorry, rod.
Okay, all right. So copper solid. Now, next, what are the electrolytes? What does the electrolyte do? Is it a common electrolyte, or are they two separate electrolytes? Are they two separate cells? Is it one cell? How is it?
Separate electrolytes. Zinc salt ka solution and copper salt ka solution.
Okay, let's first, if you want to give Daniell cell in the most efficient manner, instead of giving information in this manner where each thing is being described, what is the best way? There's a cell representation, correct?
Yes.
So let's directly go to that. Give me the cell representation for Daniell cell and explain the parts. Start.
Sudden, like the reaction should I tell?
Okay, Zn.
Zn plus Cu2 plus gives Zn2 plus Cu.
Okay. Okay. All right.
And then Zn is in solid state and Cu plus 2 is aqueous. Zn2 plus aqueous. And
Okay. This is the reaction. I ask for the cell representation. How should I represent the cell in this particular case here? Are you familiar with cell representation?
Yes, yes.
So let's have a look at some of the questions over here. It looks like they are not using cell representation much.
It is there.
Yeah, yeah. So let's take this. And let's talk about this a little bit. So in this here, as you can see better, they are using a proper representation for a cell. So you're going to be having this part here being the one which represents the oxidation, correct? So in this case here, in the current cell, Daniell cell, what is the oxidation reaction?
Zn became Zn2 plus.
Good. So we're going to be having zinc slash zinc plus 2, aqueous solid, being the way to represent the scenario over here. And we can also add one more here. You can mention comma ZnSO4. Effectively, you can mention by adding that comma ZnSO4, we are telling that it is going to be in the form of a salt, zinc sulfate. And you're also going to be having one more thing you can add as a tiny mention here, dilute H plus, because there's going to be a few drops of dilute H plus usually present in the solution here. Why do we usually have a little bit of dilute H plus? It helps in increasing the conductivity of the solution. It helps in increasing the flow of the ions in the solution. We'll talk about that when we come to conductance discussion. So conductance discussion, we'll talk about why H plus is going to be something. Adding a tiny bit of dilute H plus is very, very useful. So now let's, this is related to something called as Crothers effect. So if I forget, remind me sometime. Okay, this is something which is not necessarily technically, I don't know whether it is useful or not, but it could come out to be handy. It's a simple effect. Anyway, coming back to the point here. So zinc plus 2 is going to be in the form of zinc sulfate over here, in this particular case over here. All right. Now, the next thing over here, as you can see, there is 2 slashes. What does this double slash indicate, beta?
That they are in 2 different beakers.
Okay, all right. The double slash, technically, yes, that is basically what it indicates. You can also think of it as indicating a salt bridge. All right. The double slash can basically be considered as something which is indicating a salt bridge. And yes, another way of interpreting the same information is we can also interpret it as the anodic solution or the anodic half cell is separated from the cathodic half cell. That's effectively the idea over here. So the anodic half cell is separated from the cathodic half cell in this particular case here. So when the anodic half cell is going to be separated from the cathodic half cell over here, how is this going to be something which is going to be happening over here? Think, what is the reason why this is being done? What could be the reason? Why are we separating them? This separating them is basically making the process more complicated, correct? That is why we are having a salt bridge over here, correct?
Yes.
So what is the purpose of separating? Why don't we try to have all of it together in one bunch? What's the purpose of separating them? What do you think could be the purpose of separating them?
Continuity of the reaction.
Salt bridge is there for reaction to continue. That part you are correct. You have memorized that about salt bridge from somewhere, and your brain is saying it might have something to do with this. You're not wrong about that part over there. But that does not have much to do with what I'm asking here. What is my question related to? My question is not asking how we fix the problem which happens because of separating them. You understand what you are giving me as answer here?
Hmm.
So you gave me the answer that if I'm going to be having a problem which happens because I'm separating the anodic half cell and cathodic half cell, that problem can be solved by using the salt bridge. And what is that problem? That problem has something to do with the flow of electricity or electric charge. Correct?
Yes.
Okay. Flow of electric charge through the circuit which is helping us measure everything. Now my question goes to this. Why did we separate them in the first place? We have to have gained something in the process now. What did we gain by separating them? We had to add some extra things which made everything more. What are we gaining over here? What are we doing? What did I tell you we are doing in all of this process over here? What are we trying to do? I have a box originally where there is a chemical reaction happening. I am a human being. I want to study this box. Why do I want to study this box? I want to study this box so that I can make the box useful to me. Whatever is happening inside, I want it to be useful to me, as useful as possible. So, in the process of studying it, I have realized a few things. Things can be useful. But imagine, let's take your classes. Let's take your classes. Classes can be useful and not as effective or as efficient as well, correct? Yes or no? Right?
Yes.
That is the simple reality of the situation. So that is going to be something which is in non-negotiable, really. But at the same time, what is the way to make them better? You take control, complete control in your hands over the way to basically design your classes, your schedule, exactly correct?
Yes.
Is that not what you are doing? Is that not what your mother is doing doing for you, or you're helping you with? Right? This is not something which is happening by just one person. It's happening to a family, right? Correct?
Yes.
I know it is not something which is easy. This is going to be involving a lot of juggling of everybody's time. Now, the question is, why? Why did you do it? You gained more control over it. In terms of, when I say more control over it, you gain more control over the change which is happening now in you, and which is going to be happening to you soon. So you are gaining more control over the reaction because you took control over the reaction at every stage. And when you take control over the reaction at every stage, you can control the product more properly. Correct? Is that not what you have done?
Yes.
So if I'm going to be looking at a chemical reaction, if I want to do the same thing for a chemical reaction, what should be the equivalent part of it? What should be the equivalent of it? If I just try to show you how the metaphor would be in, what to say, the change which is happening here. So if you consider your full change through this 11th and 12th standard as a chemical reaction, all right, what have you done? You have basically taken control of the small parts of it as much as possible, so that you can as efficiently get control over the final product of the reaction. Correct?
Yes.
You understood that? I want to see your face actually, because this is a question which I have right now. So I want you to metaphorically understand this as well. So did you understand what I'm trying to describe over here to you?
Yes.
So what I want you to think now is, in a chemical reaction, what will that translate into? What do you think that will translate into?
Like flow of current, so that current can be used.
So your brain is going towards flow of current somewhere, correct?
Yes.
So now, what does flowing current give you? What is the advantage which that gives you? When you change the reaction and when you make it into a circuit, by separating it, we are making it into a circuit over there, correct? What is the biggest advantage that it gives us? Making it into a circuit. What's the biggest advantage of having a light in the form of a switch over a lamp, other than the fact that it is cheaper and more energy efficient to the environment, less polluting, all of that is there. Other than that, all of that, what is the main reason an electric bulb is more preferred by a huge margin compared to a diya?
You can control it, like when you want to.
You can control it. That is exactly, you can control it better. Literally, correct? That is a
Yes.
blunt thing. You can control it better. So what does separating the two halves of a reaction do? You get like extreme control. You can stop the reaction exactly when you want. Basically, in every cell, you draw that key, right? Just for the sake of drawing it. Why do you draw it? Why do you draw it? Have you ever thought of it? That was the thing which the scientists could control. That key was the entire purpose of that experiment. The entire experiment was done so that that key could be put there, so that we could switch on and off the reaction whenever we wanted and control every bit and part of it. And we could study it in extreme detail. When I'm having a reaction happening where I can control when I start and stop it, what does that give me? What can I do then? Think of it like this. I'm trying to study a chemical reaction. Okay, I'm trying to study a chemical reaction. This chemical reaction, I want to see what's happening inside the box. Okay. So if I want to see what's happening inside the box, how do I find out what's happening inside the box? I'll have to use some mathematics. I'll have to use tricks. So I'm first going to be looking at what to say in this particular case here. I forgot where we were talking about. This goes into equilibrium. My brain went there. I'm sorry. What was the point I was trying to explain here, Kana? Can you bring me back on track?
Key के बारे में.
Hmm?
Key, like control the reaction.
Controlling the reaction. Okay. So the circuit over here basically allows us to control the reaction perfectly. So because the circuit can allow us to control the reaction perfectly, we can then study the reaction at every instant. Like I can say at this point, this much of the reaction has only happened because I only switched it on for this much amount of time. You understand the idea over here? So because I can control, I also know how much is being sent in. So controlling also means measuring exactly what you are doing there. Give me a second. Let me turn on the light here. Yeah. So in this particular case here, the control basically also means we are literally having what to say, the ability to know how much is going in and out also. Literally counting what is going to be happening in a reaction. Of course, this level of understanding and control was only possible when it came to reactions of one type. What type of reactions could we exert this kind of control over? Reactions which involved electrons. Can you tell me what those reactions are called? Because Technically, only those which are involved in that flow of the electric charge we can control, correct?
Yes.
Right. So only the reactions which involve electrons, we can turn on and off. We can basically switch it on. We can separate the two parts because this part has to exchange electrons with this part. Physically, they have to exchange stuff for the reaction to happen. So how do I control? I separate them out completely. And then I give them only one pathway through which they can connect. You understand what is the idea over here? So this part of the reaction and this part of the reaction technically are going to be interacting with each other. But they are not interacting directly right now. They don't look like they are interacting directly. But they are actually interacting directly. Some stuff from this is interacting with some stuff from this. It is just through a path which we cannot see. So what is being transferred around? Electrons have to be moved around. What are these reactions where electrons are moved around? Redox reactions.
Redox.
So the only type of reactions which we can actually chemically control, the chemical reactions which we can control, where we can exert a lot of control over the chemical reaction, those are the reactions which we can study in greater detail also. Because reactions happen too fast. If I want to study, how can I study something which is happening so goddamn fast and understand it properly? You understand what I'm trying to tell you over here? Say, for instance, what is the reason why you are taking this kind of individualized classes? Mainly because the regular routines which are available in your place are not sufficiently suitable in some way or another with respect to what your preparation requirements are, correct?
Yes.
I mean, either somewhere or another, I do not understand, or rather I cannot claim to understand what is not fitting, but in some way or another, if I consider what is available in your vicinity and where your circumstances are right now, they are not exactly merging perfectly. So you require a little bit more from the outside over here. In a similar way here, when you end up having a reaction where you know there is a point of issue, you can then start controlling it. That was what electrons were. So when scientists were looking at a reaction and they were trying to see how to control reaction, they had to really go in depth over there to see, and then only they could control the reaction. And basically, the person who will know what to say themselves best is yourself. You will know your own requirements best. So it's always going to be best when you're going to be having what you're having, whatever you're doing now. Basically, I take the role of, I suppose, a personal tutor, correct? Somebody who basically, wherever you see in your whole picture, jahan pe gaps hai, serious gaps hai to serious hai, kam hai to kam hai. But somebody has to have a clear picture of the whole and then fill it up, correct? But that requires somebody who has a fuller picture of the whole thing. And somebody who has a full picture of this and somebody has a full picture of this. You have a clearer understanding of who you are. I have a clear understanding of the subject. So we can merge them together cleanly over here. You understand the idea over here? So effectively, when scientists started looking at reactions, they had to look at, I want to combine, I want to understand reactions, I want to study. They started seeing control was necessary. Then they started saying, oh, electricity is something which I can try to marry with this. This was electricity starting. Then electricity and control basically merged together. Then they realized, oh, this is win, 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 win. Let's now go electricity fully. And they started going deeper and deeper and deeper into electricity. That's basically how electricity started developing as a field. And from where electricity was being used to study chemical reactions, it became the other one which started dwarfing completely. So initially it was like chemical reactions was being married with electricity. But then electricity became so goddamn big, it just blew everything out of the proportion over that. Electricity was a small one there at the starting. Chemical reaction was the big one. And they were chemical reactions were the big field. They were being merged together. Then when electricity took off, you can see where electricity has gotten us. So yeah, that was like that's basically what I was trying to anyway talk about over here. Let's come back to the chemistry of it now, and story से निकलते हैं. So when you're going to be having a chemical reaction happening over here, the salt bridge over here is going to be talking about the separation over there. It is going to be talking about how to connect the separation, and you're correct over there. The salt bridge is something which is going to be disrupting the it is helping the flow of electric charge go more smoothly. So why is the salt bridge necessary? The salt bridge becomes necessary because when you end up having an anodic half cell and a cathodic half cell, in this case here, let's take the zinc itself. So this is going to be a zinc rod dipped in a zinc 2 plus solution. Okay, now, and the next thing is going to be here, we are going to be having a copper rod dipped in a copper sulfate solution. You'll be having a tiny bit of dilute H plus here, you'll have a tiny bit of dilute H plus here. Okay, so when you're going to be having this as a situation over here, what happens now? So in this particular case here, you're going to be having these two being connected by the cell. So there will be a bulb here. I suppose I should have drawn it a little bit better, but chalo, a bulb will be over here, and we'll end up having this as the cell. Okay, so you're going to be having this as the cell here. Now, when you end up having the reaction happening, you're going to be having zinc 2 plus here is going to be produced as the zinc rod dissolves in. So as the zinc rod is going to be dissolving into the solution over here, what is actually happening is going to be that you're going to be having in this solution here, zinc plus 2 concentration keeps on increasing. Okay, it keeps on increasing. Okay, so if it keeps on increasing, what is supposed to be happening here in the process? The zinc is supposed to dissolve and become zinc 2 plus, and it should kick out electrons. Those electrons are supposed to flow through this circuit. When I turn the switch on, those electrons will flow through the circuit over here, and they will reach this copper electrode. So far clear?
Yes.
And if they are basically going to be reaching the copper electrode, then the bulb will glow. That's the idea here. So now when they reach the copper electrode, what is going to be happening in this particular case over here? The copper part over there is going to be the copper plus 2, which is present in the solution over here, is going to be accepting the electrons, which are going to be coming through the copper rod over here, and they are going to get deposited onto the copper rod there. So we're going to be having the copper 2 plus getting deposited and becoming more copper and getting added onto the copper rod over here. That's effectively what happens. So if this is going to be happening here, let's now try to see what is going to be happening. Let's try to let this go, let this happen for some time. So if I let this happen for some time now, what's going to be happening is very simply put, in this case here, zinc 2 plus concentration, as I said, will keep increasing. And as the zinc 2 plus concentration keeps increasing, this entire region will effectively become positively charged. Yes or no, Kana?
Yes.
So if this entire region becomes positively charged, will it not pull back the negatively charged electrons that are trying to escape?
Yes.
Right. So in this particular case here, how do I measure the voltage? Let's talk about that quickly. So how I measure the voltage is I will now put a voltmeter here in parallel to this entire thing. So when I put a voltmeter in parallel like this, what is that voltmeter actually going to be measuring over here? Tell me, what is a voltmeter measuring?
The potential difference.
What does that mean? What does that mean? So what does it measure?
The voltage.
Okay. What did I tell you electrode potential is just a while back? Why did I go into tangents 2-3 times till now? What is the story I'm trying to explain here? What is a voltage measuring? It is measuring the tendency of that chemical reaction to happen. Correct? Yes. So
Yes.
I'm going to be having at the start, I will have some E value. Let's call it E naught. No, let's not call it E naught, E1. Okay, I'm going to call it E1. Okay, so if I'm going to be having E1 as the what do you say, electrode potential of this circuit, no salt bridges here by now at the starting. What will happen if I turn the switch on? The first measurement is E1. What will be happening then? My zinc 2 plus will get accumulated on this side, correct? So this side zinc 2 plus will keep getting accumulated. Positive charge keeps increasing. That will pull back the electrons to some extent, correct? So what is this voltage really measuring? It is measuring how easily the electrons are moving from one end to the other. That is what it is measuring, correct?
Yes.
So when I say tendency of the reaction to happen, what does tendency of the reaction to happen mean? Tendency of the reaction to happen basically refers to nothing but what is meant by tendency, or other you can think of it as tendency only again over here. So tendency of how smoothly tendency of how willingly would be a better way of looking at it. How willingly electron flow happens. That is basically what we are measuring over here, correct? So if the electron flow is happening more willingly, I'm going to be having what is called as a higher voltage, correct?
Yes.
If my electron flow is happening less willingly, I'll be having lower voltage, consequently.
Yes.
Right? So now, in this particular case here, Kana, come to this. What is going to be happening? As my zinc 2 plus gets accumulated here, what will happen?
Voltage will decrease.
Voltage will decrease sharply because that's going to be pulling the electrons back. Same thing over here. In this case here, what will be getting accumulated in the solution? What will get accumulated here?
Copper.
Copper 2 plus is leaving. What is it leaving behind? That will get accumulated now. What is the copper 2 plus paired with in the beginning?
CO2 plus is accepting electrons.
What is the copper 2 plus paired with in the beginning?
Copper rod.
Copper 2 plus, Kana, what is that guy's partner in the beginning? At the starting, before the reaction happens, before I turn on the switch, who was the partner for the copper 2 plus? The sulfate. So when the copper 2 plus is getting deposited and becoming copper, who is it leaving behind?
SO4.
So in this case here, SO4 2 minus accumulates. So you're going to be having negative charge getting accumulated here. So effectively, just as much as this side. On this side, the zinc 2 plus will try to pull the electron back. Here, the negative charge accumulation which will be happening will push the electrons away. So you're going to be having both sides are going to be rejecting the flow of electricity. So the voltage which you are going to be having will drop very, 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 very fast. and the cell will not work. All right, the cell will stop working very, 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 very fast. So that is the reason why people have to use a salt bridge. You understand what's happening over here? Why a salt bridge is necessary? Clearly?
Yes.
So when you end up having a salt bridge, what is the salt bridge going to be doing? That salt bridge fellow is effectively going to be something which will, of course, end up doing what here? The salt bridge will effectively end up being something which is very useful in maintaining the balance of the charges by providing a different ion to complement. So the problem here is not that zinc 2 plus is getting accumulated. Zinc 2 plus can be here, no problem. The problem is there is nothing balancing it out. So as and when zinc 2 plus gets accumulated here, in that salt bridge, we will usually be having ions, or rather we'll have a substance like potassium nitrate, KNO3. So if I have KNO3 as my substance in the salt bridge, what is KNO3 containing? It contains K plus ions and it contains NO3 minus ions. Correct?
Yes.
So when this side is getting extra zinc 2 plus, I will have NO3 minus ions going in. As and when extra zinc 2 plus goes in, for every single extra zinc 2 plus, we will end up having 2 NO3 minus ions going in and balancing it out, neutralizing that solution out immediately. In a similar way, when I'm going to be having this side here, sulfate ion starts getting accumulated. What will go inside over here now then?
K plus.
Good. So the K plus ion will now go inside over here and will balance out that sulfate over there. You understand what's happening by the salt bridge over here clearly, beta?
Yes.
So if these two are here, what will happen? Now my voltage will work properly for a longer period of time. Yes or no?
Yes.
So in the beginning, chemistry was basically looking at studying the reaction and the voltage was important. But once it became something where there was a constant voltage available, what did scientists start realizing? At constant voltage, what starts becoming more interesting? If you're able to achieve constant voltage like this, what does constant voltage mean? Simultaneously, what does constant voltage mean? It means the bulb is glowing permanently, right? And with a clean light, correct?
Yes.
So if it is going to be something where the voltage is slightly lower, what happens? The bulb will glow lower, right?
Yes.
So if we are able to get it to a constant voltage or a nearly constant voltage, we will be able to start using electricity truly. So when scientists started realizing that, what happened was all of the energy into developing electrochemical cells started going towards finding cells and making them. What should be the necessary condition? What do I want in that cell which I'm going to be making or using? What do I want? If you're buying a cell, what do you want?
Constant voltage.
Perfect. This became the mantra. You understand what's going to be happening next over here?
Yes.
So things started from Daniell Cell. Daniell Cell, they basically started with the chemical reaction. They wanted to harness the chemical reaction as efficiently as they could. In the process of harnessing that chemical reaction, they realized the best way of harnessing it is converting it to electricity and using it as potential to make it do work by glowing bulb, etc., etc., etc. In that process, what they realized was, oh, from here, constant voltage is going to be far more important. That means any electrochemical cell we are going to be making is going to be something which is going to be requiring a constant voltage. Only then is it going to be something which I can sell in the market and make money? Scientists at the end of the day are people who are interested in money just like everybody else. So scientists of that time automatically moved towards what was going to be conducive for making money effectively. So the idea here is we are going to be moving into the next part of the cells over here. I hope you understand the general story as to why things move from here to the next step. Because in the remaining electrochemical cells, what do you have as a constant trend in all of those electrochemical cells? Let's quickly have a look at this. Open and load. So the topics you mentioned were dry cell, fuel cell. So let's start talking about, let me just cut this part out and stick it there. Okay. Okay, this has been going on in a very random place over here. Okay, let's get to the next page and continue on. So when you're going to be having the remaining cells taken, most of the time you will end up having the cells having constant voltage being what we are predominantly aiming for. Let's start with a dry cell and a fuel cell. I suppose you understand what are cells in general now, yes, Kana?
Yes.
And what is the purpose of these cells and how they are basically utilized, and what is Nernst's equation? Nernst's equation is basically going to be giving us mathematically how we can what to say, understand or link up the different variables which we have, which we can calculate. What are the different variables which we can calculate as what to say, scientists who are studying this? We can effectively calculate stuff like, say, for instance, we can calculate what is the concentration present in each of the containers. We can calculate what is the voltage, and then see what connects all of them. So that is basically going to be your Nernst equation over there. How electrode potential is changing with concentrations. That is basically what it helps us in understanding. So it also helps us in connecting what is going to be the other way of understanding tendency of a reaction to happen. So when we are looking at tendency of a reaction to happen, we started off with that only. So let me give you 3 different ways in which tendency of a reaction to happen is measured or is understood by us. So tendency of a reaction to happen is something which can be measured. Theoretically speaking, one way is going to be delta G. One way of quantizing it is delta G. Another way of quantizing the same thing is going to be equilibrium constant. Another way of quantizing the same thing is going to be electrode potential. And then yet another way of quantizing it is going to be the one which is linked to the electrode potential, which is tendency, which is the definition of electrode potential actually. So let me just put it closer to electrode potential. This is actually definition of this, which is going to be tendency for, or other willingness of electrons, tendency for flow of electrons. That is effectively the idea here. So each of these 3 are basically measuring the same thing, the tendency of a reaction to happen. That is what they are measuring. So ultimately, since they are measuring the same thing, we need to have some way to connect all of them together as well. Do you understand what's happening over here, Kana?
Yes.
So effectively, the idea here is what we are trying to study is we are trying to study a chemical reaction. So I want to define, or I want to understand the tendency for a chemical reaction to happen. So how do I understand the tendency for a chemical reaction to happen over here? The way to understand it is I will have to what to say, different scientists took different paths of understanding. One scientist went into delta G aspect of it. They understood a different way of looking at it based on heat. Another person basically went into the equilibrium part of it, and yet another bunch of people went into the, what to say, control of it. And they basically ended up having one more way of quantizing the same thing, electrode potential. So each of these is basically a way of quantizing the same thing. So what are we trying to quantize over here? We are trying to quantize tendency of a reaction to happen. All of that started from there. And it started off and went into what is going to be delta G, what was K equilibrium. And from there, it directly dove into, what to say, electrode potential, which went into control. And from the control, it jumped into electricity. That's basically what happened. So let's now dive into dry cell directly. I am again getting diverted into the larger domain there. Do you understand why you have learned equations connecting each of these now?
Yes.
So the reason why you learned equations connecting each of these was because they were all studying the same thing. They were all studying the same thing. They were all trying to study the same thing, trying to do the same thing, which was quantize the tendency of a reaction to happen. So that methodology was basically done using this delta G and K. I mean, what you learn it as connection between delta G K equilibrium. What is this connection? Kana, tell me the connection. What's the equation?
Um, delta G is minus NF RTL in case.
Sorry. Delta G is equal to?
Not delta G. G naught is RTL in case.
Give me that. What is that? Delta G
Minus
naught is equal to?
minus RT ln Kc.
Good. So delta G naught is going to be minus RT ln Kc, or in this particular case here, K equilibrium. So delta G naught works out as minus RT ln of K equilibrium. Yes, that is the one I was looking for. It looks like you are struggling for a bit, but your
Yeah, I
last
was
bit
saying this
would
stuff.
save at the ending. Nice one. Nicely done. Now, how about these two over here? Delta G and the other one over here. What is the connection between these two? Electrode potential and delta G. What is the reaction here? You know this one also. Come on.
Delta G naught is minus NF E naught offset.
Good. And lastly, the reality is there will be questions sometimes. JEE में तो definitely आता है. मुझे तो तेरे question papers में तो I do not know, where they will try to link these two and ask you questions. That will basically be your Nernst equation. All right. So linking of these two is what? Nernst equation. So far from what I saw, Nernst equation, the questions are easy enough only. So they're not going to be that complicated from what I see. Now let's come to the dry cell and the fuel cell part over here and continue the discussion there. All right. So when we talk about dry cell here, so I think it'll be best to go for the NCRT part of the dry cell over here. Do you have NCRT with you, Kana? You follow NCRT syllabus, right?
Yes.
Can you just send me a photograph of the NCRT syllabus's dry cell part? You have a textbook with you now?
Yeah.
So just send me the NCRT syllabus part of the dry cell and the fuel cells. Let's start off with this now. Let me actually take it to a fresh page and discuss this. So the principles we have discussed will all be followed in these two cells over here. We'll talk about them as we are discussing them from the NCRT directly, because this part here doesn't require too much understanding, but it requires information, which NCRT gives better. You're still on, right, Prisha?
Yes.
All right, so let's continue here. So let's dive into primary and secondary cells. So I'm assuming you understand what a primary cell and its secondary cell, the basic difference is correct. Primary cell is something which is not rechargeable. A secondary cell is rechargeable. Bluntly speaking, that's the difference. So a primary cell, you will end up having the reaction being possible only in one direction, which is the forward direction. Rather, to put it very simply, the reaction is controllable in that format only in the forward direction. Remember, what is the purpose of all of these cells? The purpose of these cells is to control a reaction at the end of the day, right? So in any cell, whether it's electrochemical or electrolytic, if it's an electrolytic cell, what are we doing? We are still controlling the reaction, but we are making the reaction happen there. In the electrochemical, what are we doing? We are controlling the reaction, but that reaction is doing something for us. Instead of we giving something to the reaction, we are taking something from the reaction. So the difference is in the electrochemical cell, we take something from that chemical reaction. Whereas in the electrolytic cell, we give something to the, chemical reaction in that particular case there. In net essence, that's basically what happens. So in this particular case here, when you're going to be considering the, primary batteries over here, let's quickly have a talk on the primary battery here. What you can see over here is the primary battery is something where we can only control one direction, or the setup we have associated with that battery can control only one direction. Whereas in the secondary battery, the setup we will be having will be capable of having control over both the directions, over the electrochemical part and the electrolytic part. When you want to have a reaction, you can't just have one direction being one thing. If I have a particular reaction having one direction being delta G negative, opposite direction is automatically going to be delta G positive in that particular manner there. Which means if I want to do in one direction, I'll be gaining energy. In the other direction, I'll have to supply energy. So when you have a cell which is built in a manner where only one direction can be controlled properly, that becomes a primary battery. Something where it is built in a manner where you can control both, then you call it a secondary battery. Okay, so let's talk about primary battery and dry cell first over here. So dry cell here, the primary reaction which occurs, the reaction occurs only once, and after use over a period of time, the battery becomes dead. This is what I was basically explaining. It is basically what is meant by a primary battery here, and cannot be reused again. Wonderful. Okay. So in this case here, they are mentioning a few points over here. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. These are the main 3 points. Reasonably light, compact are both okay. But the other one, the voltage should not vary appreciably. That is a very, 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 very key point. It gets glossed over usually, but it's a very key point. Okay, all right. Now coming back to the thing here. So it cannot be reused over here again. All right. The most familiar is going to be the dry cell, which is also called as the Leclanche cell. Leclanche cell is basically named after the dude Leclanche was basically its discoverer, which is what they are mentioning here. Okay, so this is used everywhere. This is your normal pencil battery, everyday cell, whatever you want to call it. The cell consists of a zinc container that also acts as the anode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon. So what is going to be the cell here? Let's write down the cell here. So we are going to be having, in this case, the cell is going to be zinc over here. And since it is going to be the anode here, the zinc is going to be becoming zinc plus 2. Okay, all right. The zinc is going to become zinc plus 2. What is the form in which the zinc plus 2 is going to be mainly present? That is going to be ZnCl2. Okay, all right. It is going to be present as ZnCl2. What else is present over here? This is not double line. I should not have put it like that. I should have put it differently. Let me take a different color, make it thicker and put, actually no, it's fine. So this is going to be the first part now. This is the anode part right now. In the cathode part, what's going to be happening over here? In the cathode part, we're going to be having carbon graphite rod is going to be the cathode, surrounded by powdered manganese dioxide. and carbon. The carbon is of course there for facilitating the flow of electrons. In the sense, the carbon is the graphite rod, which is the electrode over there. So the electrode has to allow the charge or the electrons to basically be transferred. Okay, all right. So what is going to be happening is, in this paste over here, you're going to be having zinc 2 plus, correct? So we will have the zinc cup, this zinc rod over here. Instead of a zinc rod, we have a zinc cup. The zinc cup will slowly dissolve. A tiny bit of the zinc cup basically ends up dissolving into this inside over here. And we will end up having, as the zinc cup dissolves, it becomes zinc 2 plus. So as the zinc cup is going to be dissolving over here, how is that going to be dissolving? It is going to be dissolving technically with ammonium chloride over here, and it will effectively end up becoming zinc 2 plus ions. Let's not call it ammonium chloride there. It will not dissolve in ammonium chloride there. That is actually wrong there. So the zinc will basically end up dissolving and will end up becoming extra zinc 2 plus ions in the solution. Let's just leave them as extra zinc 2 plus. It's fine actually. So we're going to be having extra zinc 2 plus ions present in the solution along with zinc chloride. But the advantage here is this ZnCl2 is present as a solid. All right. If it is present as a solid, what's the advantage? See, have a look over here. In this particular case here, it is calling itself as a paste, ammonium chloride paste. See, ammonium chloride paste. So ammonium chloride is also going to be in the form of a moist paste of ammonium chloride and ZnCl2. What is the purpose of having a moist paste over here? So when you have a moist paste of NH4Cl and ZnCl2, the advantage is the concentrations of zinc 2 plus and ammonium ion. See, if I'm going to be considering this as the reaction, they've given you the anode and cathode reaction here, Nagana. So if you want the reaction to be something which is going to be having constant potential, that is necessary, correct? That's what we talked about. What is needed? Can you tell me for this reaction, which is given here, anode and cathode, for it to have constant potential, constant voltage, what do I need? Can you turn on your camera, beta? So for that reaction to have constant potential, the dry cells reaction to have constant potential, you have a obvious copy of the dry cells reaction with you. Tell me which parts of the reaction should you pay attention to if you want to have constant voltage? Which parts can change?
The rods we can anode cathode.
Will the anode and cathode matter? Tell me. If I'm looking at a reaction, Nernst equation. Nernst equation is basically something. What does Nernst equation help us understand? What is the purpose of Nernst equation? It helps us understand how concentration changes affect potential. Correct?
Yes.
Ultimately, that's what Nernst equation tells us. Yes or no? Not just concentration. Another thing which it also gives is how temperature changes also. It can also be used not just for concentration, how temperature change also. Yes or no?
Yes.
Temperature change ka, that RT by NF, that part. Okay. Now, in this reaction here, from that point of view, let's start talking about the zinc solid first. Will the concentration of it change? What is happening to the zinc solid over time?
It is dissolving.
dissolving. Okay. That's why sometimes if you have a battery which is like completely gone, you have it leaking sometimes, right? Okay, it dissolves. Okay, all right. After dissolving, other than that, what about the concentration? Because technically it is concentration and temperature, right? How about the
Yes.
concentration here? What's happening over here over time?
Decrease.
Hmm? Yes, Kana?
Decreasing.
Decreases. So if I'm considering the concentration of zinc, okay, you're assuming it is decreasing, correct? Now, let me ask you a very simple question over here. Calculate the concentration of zinc, please. In this case, it's zinc solid, correct? Huh? Calculate the concentration of zinc solid, please. How do you calculate it? What is concentration defined as? Moles per volume, correct? Huh?
Huh.
Right. Okay. Do I know any mathematical function for a solid which is similar to this? What do I know? What function do you know for a solid? Similar to moles per volume. Can you define density, beta?
Mass upon volume.
Mass by volume, right? Weight by volume, right? So if I can convert the weight into moles, then I'm done.
Huh.
Correct? So if I know for a solid about information about density, that information about density can be directly translated into information about concentration. Correct?
Yeah.
Because density and concentration, what are they? They are measuring the same thing. Correct?
Yes.
Effectively, just like how we talked about in the previous part, these three are basically measuring the same thing. Different ways of measuring the same thing. Same way here, density and concentration are different ways of measuring the same thing.
Yes.
समझ में आ रहा है मैं क्या बोल रहा हूँ मैम? सो अभी सोचो सॉलिड के लिए डेंसिटी चेंज होता है कि नहीं?
No.
हाँ? Will density of a solid change?
No.
No, no. If I have zinc solid, if I have say iron rod, if I have a tiny bit of the iron rod, or if I have an infinite amount of iron, the density is going to be the same, right? If it's from the same source, right? Right? And that basically means what? The zinc solid concentration does not change with time. You understand what your mistake was clearly here?
Yes.
So now, if concentration does not change, now let's have a look again with fresh eyes. So the zinc solid concentration does not change. So if concentration does not change, can it affect my potential?
No.
No. As long as what? As long as temperature doesn't change. So if temperature is maintained a constant roughly, the zinc solid here does not affect my electrode potential. Good. So one guy down. Next. How about zinc 2 plus? What is this guy present as? It's present as ZnCl2.
Huh.
What's the form of the ZnCl2? Moist paste. Which means what form is it? What's the advantage of solid?
Concentration.
Concentration is constant. So this also is taken care of. You understand where the story will go every time now?
Yes.
You understand why the reactions are so weird? No, I hope. Yes? Ideally, we would like to keep it simple, but the purpose is going to be to achieve constant voltage. So this is the reason why. MnO2 now, manganese dioxide, powdered manganese dioxide. Obviously solid hai na? So solid na, again. Ammonium, how is there ammonia present? Ammonium chloride, what? Moist paste, solid. MnOOH, solid. Ammonia, gas which is going to be trapped on the inside. And when it is trapped on the inside, it is going to be something which is present with what? It is present with ammonium ion. So again, a solid. So you're going to be having the entire thing being something which is going to be purely made up of solid substances. If you're going to be having as many solids as possible, you'll be able to maintain a constant voltage as much as you can. That's the idea over here. So is this properly clear here, Kana?
Yes.
Okay, now let's go to the actual reaction which is happening here and quickly discuss that part out over here. So you're going to be having cathode reaction being MnO2 plus NH4 plus electron giving MnO.OH plus ammonia. Okay, so effectively what's happening in this particular case is manganese here is in +4 oxidation state, and it is going to be going to a +3 oxidation state in this particular case here. So when it's going to a +3 oxidation state here, you're going to be having a reduction reaction happening in this particular case here. That's why it's gaining 1 electron in the process. At the same time, the zinc is losing 2 electrons over here. So effectively, we are going to be having this reaction multiplied by 2 and then added up. Meaning, what is my final reaction for the dry cell over here? The dry cell's actual final reaction will be zinc solid plus we'll be having 2 MnO2 solid plus 2 NH4 plus in the form of solid gives Zn2 plus in the form of a solid over here plus 2 MnO.OH plus 2 NH3. In this process over here, 2 electrons would have been transferred. So the number of moles of electrons transferred for this would have been 2 moles of electrons transferred. That's basically the idea. So if the number of moles of electrons transferred is 2, are you familiar with what is meant by N factor, Kana?
Yeah.
Define N factor.
The like in acids, replaceable hydrogen atoms.
How about for redox?
Moles of electrons.
Good. So effectively, you're going to be having N factor in terms of redox there. You're not exactly on the right path, but you're on the right path to an extent. So you're going to be having N factor being defined as N factor for redox. The best way to define N factor for redox reaction is number of moles of electrons transferred per 1 mole of substance. That's basically the idea over here. So number of moles of electrons transferred for every 1 mole of substance is basically what is going to be meant by N factor for a redox reaction. Now, what's the best way of doing this? Balanced reaction, if you have it already, check the balanced reaction and you'll get the answer directly. So in this case, 2 moles of electrons are transferred for the overall reaction, correct? So for zinc, what is the N factor? 2. And for this guy, N factor is 1. For this fellow, N factor is 1. For this fellow, N factor is 2. For this, N factor is 1. And for this, N factor is 1. You understand the idea here?
Yeah.
Okay, all right. Now let's continue on. So this is the reaction over here. We are going to be having number of moles of electrons transferred. Okay, that is also covered. Okay, ammonia produced in the reaction forms a complex with zinc 2 plus. So they're telling you that the zinc 2 plus over here is actually going to be complexating with the ammonia over there. I actually assume that it's going to be basically present with the NH4 plus, but I was wrong over here. The actual reality is it's going to be complexing with the ammonia there. So this zinc 2 plus which is produced here is actually going to be complexing with the ammonia to effectively form this ZnNH3 twice. Is not correct there. That doesn't make sense. ZnH3 4. Yeah, they have given 4 only. So that's correct there. So we're going to be having ZnH3 4 times 2 plus. Sometimes the reading itself I'm doing wrong. ZnH3 4 times 2 plus is going to be the complex formed here. So why did I stop there when I thought I read 2 there? Main reason is because zinc 2 plus only forms tetrahedral complexes. So the moment I saw ZnN, I thought I saw when I was writing ZnH3 2, I thought I saw 2 there. I realized, Anyway, so coming back to the point here, that is something you guys have coordination compounds also, Nagana.
Yes.
So you need to know about that point also. I'm hoping that you already knew it. Yes?
Yeah.
Good. Okay. Now in this case, the cell potential here is going to be nearly 1.5 volts. That's just an information. It is good to have that information because it's available in NCRT. You need to know this piece of information absolutely. Okay, that's why you need to know this complex also. This complex here is a tetrahedral complex. Okay, and it's a D10 tetrahedral complex. All right. Next, the mercury cell. We're going to be having it suitable for low current devices like hearing aids, watches, etc. Consists of a zinc mercury amalgam as anode. So zinc mercury amalgam, now we are going to be having zinc dissolved in liquid mercury. When you're going to be having zinc metal solid dissolving in liquid mercury, you'll end up having the final mixture is going to become an alloy, a hard alloy, which is called as zinc amalgam in this particular case here. That zinc amalgam is going to be the anode over here, and a paste of mercury oxide, HgO, and carbon acts as the cathode. The electrolyte is a paste of KOH, again paste. What's the purpose of the paste? So that the substances are present in something which is closer to a semi-solid state. What's the reason to have a semi-solid? So that we'll be able to have a proper cell where the potential is going to be nearly constant over time. Why is that necessary? Well, I mean, why is solid necessary for that? Because if solid is taken, concentration will remain constant. Okay, so electrode reactions are given over here. Same type. The zinc is effectively going from 0 to zinc plus 2 here. And we are going to be having, in this particular case as well, 2 electrons being lost. The HgO here has mercury in plus 2 here, and it is going to become mercury in oxidation state 0 by gaining 2 electrons in the process. So we can directly add these 2 reactions up to get the final reaction for this one over here. The final reaction for this looks like this, where we are going to be having it as, or the overall reaction is going to be simply adding the 2 of them up. So zinc amalgam, which is going to be a solid in this particular case over here, is going to be reacting with 2 OH minus. Where is the OH minus coming from in this case here? It is a paste of KOH and ZNO. So the KOH is going to be something which is going to be producing this over here. So this is solid in the form of KOH. Okay. Along with what else is the other reactant here? HgO is going to be the other reactant, which is of course going to be a solid as well over here, solid paste of that over here. And we are also going to be having water as the other reactant in this case. Now, when you're talking about water over here, that is where things are going to be getting a little bit interesting. Water, as you know, at a given temperature is having constant density as well. So in this case here, the water will of course be, if it is present in the liquid form over here, so its density is going to be more or less the same, and it is not going to be changing as well. So if the liquid's density is a constant, it will also not be affecting what the potential of the cell over here. So this liquid is also perfectly fine. All right. And lastly, what are the products over here? We are going to be having zinc oxide, which is a solid over here. So zinc oxide solid is of course going to be something where there's no problem. Water, which is going to be a liquid as well, is not going to be having any issues over here because it's also having a constant density. Mercury liquid is also perfectly fine. And the OH minus, of course, what is that present as? That is of course present in the form of KOH. So this is going to be also a solid. KOH is going to be the source of this. So this is your overall reaction here for this cell. And as you can see here, you're going to be having this cell being something where we have all of the systems which are playing a role being in solids or liquids, which means their concentrations are constant. So if the solids concentrations are constant, the cell potential becomes constant as well. So this is going to be for your mercury cell here. Let me copy the next part as well, so that the next part also can be directly discussed. Mercury cell, I think this is more or less the last bit over there. Next is going to be the secondary batteries over here. So let me copy that part. So when you talk about the secondary battery beta, how will that work? What is the purpose of a secondary battery? The purpose of a secondary battery is to run both ways, right?
Yes.
Today till what time are you free, Kana?
Sir, you can take. You can teach.
Okay. Okay. All right. So the secondary cell here is something where we are trying to do both the electrochemical part and the electrolytic part here. Correct. We have to charge it in both ways. Now, if we are going to be having charging in both ways to be considered over here, then we have to design a cell where that can be done properly. That is the reason why secondary cells are definitely more costlier than primary cells, because it can do both and it is far more efficient at basically utilizing space. So usually when you're going to be having rechargeable cells, they are inherently going to be more expensive. So let's start off with the lead storage secondary cell over here. That's the one which we have over here. So a secondary cell is something where you can recharge it after using it for some amount of time by passing current in the opposite direction. So it can be used again. A good secondary cell can undergo a large number of discharging charging cycles. Right? So effectively, a good secondary cell is something which can be used many times. So that's the purpose of a secondary cell. Okay, all right. So let's continue here. The most important secondary cell is the lead storage battery. This is something which may be changing, because the fact is the most important secondary cell of the current modern world is not the lead storage battery. What is the most important secondary cell now? Beta, are you still on the call?
Yeah.
So, are you living in the modern world? What is the most important secondary cell in the modern world now?
Mobile.
What is it?
Mobile phones.
What is that? What is that? What is that?
The battery of.
Lithium-ion cell.
Uh-huh.
So the most important one currently, this statement alone, I will not agree with this statement. The most important current one is actually going to be lithium-ion. Secondary cells, the best one currently, the most important one is lithium-ion cell. Anyway, coming back to this now. So lead storage is our syllabus is one, which is designed a long time back. So let's start off with lead storage. It consists of a lead anode and a grid of lead packed with lead dioxide. Okay, all right, as cathode. So effectively, lead anode is going to be taken and a grid of lead dioxide as cathode is taken. A 38% of solution of sulfuric acid is used as an electrolyte. Okay, so 38% solution, they are being very specific over here. I'll explain why they are being very specific in a minute when we are discussing the reaction. Okay, so the cell reactions when the battery is in use is given over here. So what is happening over here is you're going to be having anode is going to be lead here. So we are going to be having lead solid reacting with SO4 2 minus aqueous. Where is the SO4 2 minus aqueous coming from? This is of course coming from your sulfuric acid. All right, so from sulfuric acid, you're going to be having this coming. This is basically going to be giving me PbSO4 solid, which is going to be a white salt, white precipitate. you'll actually have it as a salt precipitate on the cathodes on the inside over there. Plus, of course, we'll be having 2 electrons being kicked out. Okay. Now, the next thing over here is going to be when you're going to be considering the anode reaction over here, this is basically something where oxidation is, of course, happening. Now, when we're going to be considering the cathode reaction next now, in the cathode here, the opposite has to happen. The acceptance of the electrons has to happen. So when we talk about the cathode reaction there, what has to happen over there is the PbO2 here, which is in solid form, has to react with my SO4 2 minus. Of course, in this case, is also going to be in aqueous form over here. Now, as you can see here, the reaction is also having a 4H plus over here and 2 electrons. So let's talk about what is happening here. Why do we have all of this 4H plus 2 electrons, all of this stuff? Why is it coming in actually? Now, when you're going to be having the reaction here, let's break the reaction down quickly here and just talk about it. So PbO2, the solid is going to be reacting with sulfuric acid aqueous from H2SO4. All right. And we are going to be having the reaction here producing again PbSO4, which is a solid. This is the reaction. Actually, this is sufficient. And of course, we will end up having water as well. But let's talk about why the water is supposed to be there. So PbSO4 solid is produced over here, correct? So in this case here, this is going to be the same white precipitate, nothing different. So this is technically going to be something where you can think of it as a con-proportionation reaction. So why is it a con-proportionation reaction? Because technically speaking, we are going to be having Pb becoming Pb plus 2, and we will also be having on the other direction there Pb4 plus also ends up becoming Pb plus 2. So in this case here, as you can see, the Pb plus 4 here is actually becoming a Pb plus 2. So effectively, we had a Pb0 becoming a Pb plus 2, and a Pb plus 4 also ends up becoming a Pb plus 2. That is the overall essence of the reaction. So this type of a reaction can be thought of, and it is called as a con-proportionation reaction. You're familiar with disproportionation, yes, Kana?
Oh, yeah.
So now let's dive into, you're familiar with disproportionation or not, beta?
Disproportionation.
Haan.
Haan.
Okay, so in this particular case here, when we are going to be having this reaction happening over here, what is going to be happening in this particular case here? You're going to be having, as the process happens, there, okay, I have to show the balancing part here. Na? Balancing ka dikha deta hu. So here there are 2 oxygens extra over here. We're going to be having, in this particular case here, water has to be added to balance out the oxygens. So 2H2O, so you'll effectively end up having a 4H plus on this side to balance out the, 2H2O over there. And of course, you're having plus 4 becoming plus 2. So you have to accept 2 electrons as well. So you're going to be having this as the reaction here. So you understood the balancing as to why I added 4H plus, etc. It's acidic medium balancing. I think we had discussed acidic medium balancing in one session, correct?
Yeah.
Now, so in this case here, the overall reaction has been beautifully given now. Have a look at the overall reaction here. So we have it as something like this. Now tell me if the overall reaction is in the discharging mode, which is forward direction. So forward direction for this reaction here, the forward direction is basically electrochemical, and it is called as discharging mode. Okay. And the backward direction is going to be something which is going to be called as the charging mode. Okay, so in this particular case here, we are going to be having the cell here, this electrochemical cell over here is something which is going to be meaningful in the forward direction, whereas the backward direction, which is the charging mode, is actually what kind of a cell? An electrolytic cell. You understand the principle here, Kana?
Yes.
Okay, good. So now let's continue on over here to the next part here. So on charging the battery, the reaction is reversed and PbSO4 solid on anode and cathode is converted into Pb and PbO2. Effectively, what they are telling you is the exact full reaction is going to be happening in the opposite, in the charging side. You understand the principle there? That is the exact full reaction. Now the exact thing will happen in backward. Over here as well, the exact thing will happen in the backward direction here. And over here, this exact thing will happen in the backward direction over here.